say. All right. Example 5, they say proof by contraposition. Now, what is contraposition? We say that, if you recall, we've done this already when we did propositional logic. We say that the implication, so A implies B, is logically equivalent to its contrapositive statement. And the contrapositive statement is not B implies not A. All right. I hope that you guys remember that. You see, everything is a building block. What we did the previous week, we're using them again. All right. That is the power of logic. It's a building block. So A implies B is logically equivalent to not B implies not A. All right. Okay. Not to be. All right. So not B implies not A. We call this a contrapositive statement. So one way of proving that the statement A implies B is true is to prove that its contrapositive version is also true. All right. So if I give you something like this and it's difficult to prove that it's true, then think of using the contrapositive statement and show that it is true. All right. Let's look at example 7. So for example 7, they say let x be an integer. All right. Then I say prove that if x squared is even, then x is even. All right. Guys, if you notice it, some of you when you see even and odd, the first thing you think of is your direct proof and proof by cases. Guys, be careful, because this is a very new example or new kind of proof that you haven't seen before. Now I'm giving you an implication here, all right, which is something that you haven't seen before. So don't try and use proof by cases or direct proof, because it's not going to work. All right. So I'm giving you A implies B then, where your A stands for the first statement, X is even, and your B is the statement X is, if X squared is even, then B stands for the statement X is even. So the first I'm going to say let A stands for the statement X squared is even, let B stands for the statement X is even. Then the statement is such that A implies B. Everyone is happy, right? That the statement is in the form A implies B, because I say if X was even, then X is even. That is an implication. What is a contrapositive? The contrapositive is not B implies not A. I want to see this, not B implies not A. That is, if you say not B, remember it means you need to negate this statement there. What is the negation of X is odd? The negation of X is even is what? X is odd, right? And the negation of X is odd is what? X is even. So in this case, not B, you go to B. B stands for the statement X is even. Not B means if X is now odd, then, okay, we also need to negate A. And A there says that X squared is even. So the negation will be X squared is odd. All right. I hope everyone is happy. When X is odd, what does that mean? X is odd means we can let X to be some 2m plus 1, very important, plus 1 to show that it's odd, where m is an element of integer. What is X squared? If you square that out, you factor out, you see how it works out. There's the 1 that is a standalone. It's already there on its own. There's a 1 there. Just factor out 2 from what is left. And then you're good to go. So if you factor out the 2 there, you can conclude that X squared is odd. All right. And that is true because everything in brackets here is an element of integer. All right. And then we say, since our contrapositive statement is true, it follows that the original statement is also true. And this comes from logical equivalence. Remember, logical equivalence say if the contrapositive statement is true, therefore the original statement is true. If the original statement is true, the contrapositive statement also has to be true. All right, I hope everyone is happy with that example. We almost done. Let's see, there's example 8. It's also a very easy one. They say prove the statement by proving. So yeah, I made this so easy. They say prove the statement by proving that its contrapositive is true. All right, so I tell you exactly what to do. So if m squared plus n squared is not equal to 0, then m is not equal to 0 or n is not equal to 0. As usual, do yourself a favor and just let A to be the first statement. M squared plus n squared is not equal to 0. Let B be that statement. M is not equal to 0. or n is not equal to 0. You know already that the original statement is of the form A implies B. All right, that's how your original statement is. What is a contrapositive? Contrapositive statement will be not B implies not A. And now, what is not B? All right, so not B, I have to negate. I have to negate B. M is not equal to 0. What's the negation? Negation is M equals to 0. What's the negation of R? It's N. What's the negation of N is not equal to 0? It's just N equals to 0. All right, we say if all of this, then we also need to negate A. So A that says M squared plus N squared is not equal to 0. The negation of that is just M squared plus N squared is equal to 0. All right, so I guess this is the easiest proof because if M is 0 and N is 0, what is M squared plus N squared? It would just be 0 squared plus 0 squared, which is just equal to 0. Therefore, it follows by the contraposition that A implies B is also true. All right, so what I'm saying in conclusion here is, therefore it follows that the original statement is also true. So if the contrapositive statement is true, it follows that the original statement A implies B is also equal to true. All right, it's also true. All right. If everyone is happy, let's look at the last part, which is disproof by counterexample. Guys, if I tell you to prove that something is false, all right, so the only foolproof way to prove that something is false is just by looking at one example that makes it non-true. When I say not true, it means false, all right? So if I say, show that this thing is false, just find one example, all right, that actually makes that to work, and you're done. So when it comes to disproving, you just need the counterexample, all right? Don't show me direct proof and so on, those things on why. So just do counterexample. So for example, let's look at example 9. They say disprove the following statement, right, by providing a counterexample, which makes it false. So yeah, again, I've given you too much information. In a typical test scenario, I'll just say disprove the following statement. Done. Right. For every integer n greater than or equals to 1, I say that if n is odd, then n squared plus 4 is a prime number. Okay, let's try. We want n greater than or equals to 1. So let's start with 1. If I plug 1 in that formula, n squared plus 4, I'll get 5, right? Is 5 a prime number? The answer is yes. So that is not a good counterexample. Counterexample means you want something that makes it false, actually. So let's try n equals to 2, right? You don't have to show me all of this work. You just need to show me the one that works, all right? Just show me just the one that actually works. So now the question is, we can't even use 2, all right? So don't use 1, 2, 3, 4, and so on. You can use 2 because the condition is that for n greater than or equals to 1, n needs to be odd. All right, so your only possibility there is 1, is 3, is 5, is 7, and then is 9, and so on. All right, so these are your only possibilities. But if you take note for all of these numbers, you actually get prime numbers. So let's see for 3. 3 squared is 9, 9 plus 4 is 13. Is 13 a prime number? Yes, again, that's a terrible choice. If you choose 5, you have 29. Again, it doesn't really help you, it's a prime number. If you choose 7, you have 7 squared 49 plus 4, you have 53. Again, it doesn't help you, it's a prime number. But look at the one that I choose 9. There we go, this is a nice one. 9 squared is 81, and then if you add the 4, you have 85. Take note, 85 is not a prime number. Why? Because we say by definition, a prime number is a number that has exactly 2 factors or has only 2 factors, which is 1 and itself. 85 has, you can guess already, is divisible by 5. All right. The fact that it has at least 3 factors, it means that it's not a prime number because divisible by